Hi, this is Stephen, and in this video, we will use the simplified Bernoulli equation to estimate pressures in the heart, specifically the right ventricular systolic pressure, or RVSP. And this is actually the first time we're going from measurements of velocity to pressure, so very important concept for echocardiography. You can see I've got the apical four-chamber view here. Let's look at the Bernoulli equation itself, though. And so the Bernoulli equation says that if you have your pressure at a first point plus 1/2 times the density of your fluid, that'll be blood, times the velocity at that point squared, plus the density of blood times the gravitational constant times the height at that point, that is equal to all the same values at a second point, namely the pressure plus 1/2 times the density of blood times the velocity at the second point squared, plus the density of blood times the gravitational constant times the height at that second point. And so we can pick two different points in the heart and use this equation to our advantage. Now, how can we simplify this equation? Well, if we're talking about height in meters and velocity in meters per second, then this density times gravity times height, this is pretty meaningless, and this is pretty meaningless, right? The whole heart is much less than a meter tall, and these will be fairly small, inconsequential, right? The blood is not going to a significantly different height as it goes from different chambers in the heart. And so we can rearrange this, and so I'm going to say pressure 1 minus pressure 2 is equal to 1/2 times the density of blood times the velocity at the second point squared minus the velocity at the first point squared. And again, thinking about units here, if we have blood at a first point that is going at less than 1 meter per second, let's say it's 1/2 meter per second, as you square that, you're going to go from half to an even smaller fraction, right? 1/2 times 1/2 would be 1/4. And so as long as we have our first point of velocity is going at a relatively lower rate, this will disappear to 0. Let's plug in some numbers here. So equals 1/2. The density of blood tends to be fairly constant. It's around 1,060 kilograms per meter cubed. And then I'm going to divide this by 133.3 pascals per millimeter of mercury, because we're more comfortable talking about pressure in millimeters of mercury. All of that times V2 squared, which 1/2 times 1,060 divided by 133, that ends up being about 4. So equals 4 V2 squared. So in other words, the first pressure minus the second pressure, for all intents and purposes, is roughly equal to 4 times the velocity squared. What does that mean in terms of the heart? Well, let me go back to this apical four-chamber view, and we have a first point here. I'm going to call this the high pressure, pH. And we have a second point here, the low pressure. And we can measure the velocities right at that valve. So I'm going to put my Doppler tracing right there, and I'll get a graph that looks something like this. It will show something like, during systole, you'll see a jet of tricuspid regurgitation. And you'll be able to figure out what this, be able to measure a Vmax here. Let's say for now that the Vmax equals 2 meters per second, right? So the y-axis, this is meters per second, and our x-axis is second. What the Bernoulli equation is telling us is there is a reason why blood flows from the high pressure area, the right ventricle during systole, to the low pressure area, the right atrium. And the reason is that pressure difference, and the pressure difference will then lead to a particular velocity. So let's look at this in the equation format. So in other words, the high pressure minus the low pressure is equal to 4 times the velocity, the regurgitant velocity through that tricuspid valve squared. Or I can say that the high pressure, namely the right ventricular systolic pressure, is equal to the low pressure is the right atrial pressure plus 4 times the tricuspid velocity squared equals right atrial pressure. If we say that that was normal, that would be around 5 plus 4 times 2 squared. 2 squared is 4, 4 and 4 is 16, which equals 21 millimeters of mercury. So, and just because this is such an important point that bears repeating, I'm just going to over here draw again. You've got your high pressure, and blood shoots down through the leaky tricuspid valve at a particular velocity, and it goes down to the low pressure. And the Bernoulli equation says that if you know the velocity, you can do 4v squared, and that will be the difference between the high and the low pressure. Okay, so it's all related. You go from a high pressure to an area of low pressure, and the blood, as it's flowing, the velocity at which it flows from high to low pressure is directly proportional to the difference. If you have a very high pressure and a very low pressure, then the velocity will race through very fast. If your high pressure and low pressure areas are almost at the same pressure, the velocity will be very slow. Blood will kind of sluggishly go from the high pressure to the low pressure. Hopefully that concept makes intuitive sense. One other point that I'll just mention is that we over on, if I go back to this red graph, you notice that I use the Vmax. The computer can actually, so our Vmax can be helpful to figure out our peak pressure gradient, but the computer can figure out what the mean velocity is, and it can use that mean velocity to figure out a mean gradient. So we typically in our quick calculations, Vmax to the max pressure difference, but the computer can actually figure out a mean gradient as well. And so that's how we can use the simplified Bernoulli equation using what we know about the density of blood, the fact that your velocity in the ventricle, that's pretty much negligible, the fact that there's very little of a height change. We can use that to greatly simplify the Bernoulli equation such that if you tell me the velocity of blood as it flows from point A to point B, I can take 4 times that velocity squared, and now I know the pressure difference between point A and point B.